So we have a question here, and let me draw the picture here. That's x-axis and y-axis. Okay. I have a curve. This is just a piece of curve, okay? And this is a 1. That's 2. So here's 2 and the 4. So y equals x squared. So the curve is y equals x squared, and this is the whole region we're going to use. So I'm going to rotate this region about this y-axis. So the solid is generated by rotating this region about the y-axis. Okay. So from outside, it looks like a cylinder, right? So what you got is something like that. But inside, there's another hole here. Yeah, that's a picture, right? The question is how to find the volume. Yeah, set up an integral for the volume. Okay, please do this problem. Okay, you see that, right? You like cylinder. When x equals 2, y value is 4, and x equals 1, y value is 1. So that's the point. Well, it's clearly this is a surface generated around the y-axis, right? Rotated around the y-axis. So y-axis is going to be the axis you're going to use for integral. So your idea is here is the volume is going to be integral from 0 to 4. A over y dy, right? And this is an axis. And you get a cross section. The cross section depends on where it is. Okay, so this cross section, is going to be like a circle. This moves another this side. But when is this section moving down, after you pass this circle, you get a whole disc. No, a disc with a fixed hole. Okay, the size. So the inner circle changes over here, but the inner circle will be fixed. Right? Anyway, so the typical cross section will be the larger disk and the minus a smaller, right? So this is a cross section, a typical cross section. Okay. So I'm going to denote
So this inner, this is capital, right? So a of y is going to be pi capital R squared minus little r squared. Okay, so let's figure out what is capital, right? The capital is constant. It is fixed. If you look at the picture, the capital I is going to be this part from here to here, capital. The little I is here, right? It depends on where it is. If you want to draw the picture here, it's going to be here. This is little I. Okay. Right? So the capitalized 2, clearly. But the little I depends the y value. If the y value is between 1 and 0, okay, the little r is constant, 1, right? But if this is a point, an arbitrary point on the curve x and y. If if y is between 1 and 4, okay, and the little I is going to be the x coordinate of the point. But this is not a function of y. I have to explain it in terms of y. So I know y equals x squared. So x is going to be square root of y. That's it. Okay. So that is that. And volume is going to be the integral from 0 to 4, right? Pi r squared. I is 2, so 2 squared minus pi. And this is we don't know yet, right? So it depends on the y value. So if y is from 0 to 1, then this is going to be 1 squared dy. If it's from 1 to 3, it's still 4, but here square y square dy. Okay, so you can evaluate this integral. Okay, let's finish it part. So this part is 3 pi because 4 minus 3. And here, the integral, it's 4 minus y dy. So the antiderivative of that is going to be pi 4y minus half y squared. Let's finish this. And 4 times 3 minus 1/2 times 3 squared. All right. Why is it 3? Actually, it's 4. I'm confused. It's 4. It's from 1 to 4. Okay, the interval is from 0 to 4. Y variable, right? It's from 0 to 4. Yeah, so it's so after you simplify, you get the answer, right? So let's look at how many pi's here. Let's see. Okay, 3 pi plus 16 pi minus 8 pi minus 4 pi plus half pi. So so 16 minus 8, 8 minus 4 is 4, 4 plus 3 is 7 pi. So the answer is 15 pi over 2 if computation is correct. All right. So it's pretty complicated. If its radius is defined by 2 pieces. In geometry, we have another formula for the. We have another formula for finding volume. The idea is pretty simple. Okay, so this is called the cylindrical Shears method. But this is a solid. Okay, it's not necessary to be round. I just draw the arbitrary picture. Okay, what I'm going to do is I draw in a line. Okay, this is coordinate line, and I consider this is a project here to here to here, right? Okay. So what I'm going to do is I'm going to use a cylinder to cut this solid. Most of the time, the solid is going to be symmetric around this axis. Okay. So this is this is R. We find out, okay, if this surface is a surface area, the area of this is also cross section, the cylindrical cross section. Okay, it's not like a flat. It's a flat knife to cut. Right now, you fix the straight line, and you look at the cylinder around that was radius up, and this portion inside this solid has an area of the cylindric, let's say cylindric surface, okay, which is cross section. Okay, then we find out the volume is going to be the integral of AR. We still have the same formula. Okay, we still have the same formula. It's interesting, right? But then depends on how the range. Maybe this side is open. You know, it really depends on whether, yeah, the other. If there's no intersection, then the surface area is going to be 0. So it depends on. There's an interval for R. Okay. So that's the formula. Okay, you can show that in mathematics it's true now. What is the geometry meaning of this? This means the cylindrical shears, okay, and the di is the thickness of cylindrical shears. The cylindrical shears, if we know the surface area, then multiply by di, that gives us the volume, that's the slice. So in other words, you're going to cut the solid by circular knife and expand it gradually. Okay, you know, when you make a hole, right? Cut it. One slice, but then it's getting large. So each slide, how do you find the volume? The thickness times the surface area of this slide. Okay, that's the idea. When you open one slide, see, this is open, right? One slide like that, maybe, right? And when you open it, if the thickness is like, you know, then when you open it, it goes to pieces, right? Stretch a little bit. So if this is a dr, then the thickness here is also dr. So the surface area here's AR, right? That's AR. Okay, the surface area times dr gives the volume. Okay, so now you have so many slides, but circular slides, and add them together. It's the same idea. Instead of use a flat knife, we use a circular knife to cut the solid. All right, so now I'm going to cut using this to do the problem, okay? So let's go back. Here's a picture. And this is a parabola, right? Okay, so this is a solid. Instead of cut it into discs, use a flat knife. The original was cutting like that. Slice, 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 right? And cross section is the cross section. If you know the area, right? The cross section is the area cross section is denoted by dy because it depends on the value you choose. You choose a point y and you get slice. Choose another point, you get slice, right? Now this time, I'm not going to cut this one. I'm going to design a circular knife to cut it. So what I'm going to cut is, I'm going to use this. Let me use a different color. A typical cool, right? So this is what I cut. Imagine, right? Every time I get a cylinder. So the radius is going to be R. Okay, clearly R is between 1 and 2 because this is a 1, this is a 2. So the largest possible value is, right? For each given R, can I find the area of the cylinder? I think if this is an H, okay, the area of that R is going to be 2 pi R times H. Okay, right? Yeah, how do you find the surface area of the cylinder? Circumference of circle, because when you open it, you get a rectangle. You use a scissor, right? Cut. That's from here, you open it. And the length is 2 pi R, H is the height. All right, so that's it. You know, then the volume is going to integrate from 0 to 1 to AR dr. Okay. So I have to express H in terms of R. That's easy to do that because this is an arbitrary point, right? H and R related by this is a graph y equals x squared. So H is height when x equals R, right? If x equals R, okay, and the H is going to be y, right? From the picture, I can tell. And I needed to, doesn't matter. So y is going to be x squared. So H should be R squared, right? Yeah, right? So it's going to be, 2 pi R, H is R squared and dr. Okay, you can express H in terms of. So what I got here is going to be R cubed. So the entire derivative R cubed is going to be a quarter R to the 4th power. Okay. So the 2 to the 4th power minus 1. Okay. What I get is 15 over 2. Sorry, 15 over 2, not 15. Did I get the same answer? Let's compare. 15 pi over 2. Yoo-hoo, get same. 15 pi over 2. Okay, so this new equipment that we designed, cut the solid, it's good. You get the same area. Okay. There are many ways to cut, honestly. I can use a spherical knife to cut it. When I'm saying that, because this is not, here is not talking about, we only have a washer disc method, cylindrical method, right? But actually, there's another way to cut it. It's not mentioned in the book. Use a sphere. You expand the sphere. Okay, if we expand the sphere, and then every time, yeah, think about this. Okay, this is a, but we can do that as a method. Think about that. You have a solid in the space. Every time I can choose arbitrary point. This may be not a center. So I'm going to design a knife. This is called strike knife. Every time when I draw the sphere around the center, and then getting larger and larger. But there is a cross section here, right? If this is radius r, the cross section is a, the surface is a. Okay, and then it to be surprised, you know, if you increase a little bit, and the thickness is dr. Okay, then AR times dr, you integrate it, gives a volume. Okay, it's the same idea. But this time you fix point. You look at all the points with the same distance from the center, and then you will get section around, yeah, cross section. Then you increase the radius a little bit. Then you get another straight shear. And that slide, every time we cut it, gets slide, right? And then the volume of that slide is the surface area times dr. I'm pretty sure, yeah. Then you evaluate, you get this. And depends on the r is between 0 and r. Okay. This is a useful formula. Okay. For example, how to find the volume of the sphere. Right? Yeah, here's a sphere with capital R. Okay. Find the volume. Right? What you can do is, you have to know the surface area of the sphere. Okay. So what they do is you take radius. Okay, and this is radius r. Okay, so r is between 0 and the capital R. Okay, and the surface area, okay, is going to be, it's a sphere of radius r. It's going to be 4 pi r squared. Right? Yeah, you have to assume that you already know the area of the sphere. Then you use that to find the volume of the sphere. So the volume is going to be integral from 0 to capital R, AR dr. Okay. So the volume of the sphere is just the integral of the surface area of the spheres, exhausting all the region from handling the sphere to one side. Okay. So that gives you 4 pi r squared divided r. The entire derivative is r cubed 3, and so the answer is 4 pi r cubed over 3. So it's not surprised why there's you have to divide by 3. See, remember the formula for the volume area is 4 pi r squared. Why the volume is 4 pi r cubed divided? R cubed is reasonable because it's cubed, it's volume, not it's cubed. Why divide by 3? It's come from the integral, okay? Yeah, so actually, the book only tells you 2 useful methods. One is called the disk method, another one called the strike method, a cylindrical Shears method. Okay, and actually you can have a 3 different methods. Now, how to get a disk method? So disk method is, we were talking about the distance function to a plane. Okay, so you have a plane, and it's a distance function to the plane. If the distance equals 1, then you get another plane. That's why you get a plane, another plane, plane, okay? But you can also talk about the distance to one line. okay, then the same distance to one line is a cylinder, okay? That's why, yeah, this the method comes from is here's fixed the plane in 3-dimensional space. The distance, okay, gives the same distance. It's the same distance, let's say distance equal to r. And you get another plane. Okay, when r changes, you get family of planes. And if here's a solid, then you get a cross section. That's what I call disk method. Okay, so we actually use a distance function to get the volume formula. And then this is a fixed plane. Okay, this is a fixed plane. Then we use a fixed line. Okay, if a fixed line, then the distance function is going to be r actually gives a cylinder instead of a plane. Okay, that's called. Then you get, yeah, if the surface area, if here's a, if this is a portion that gives the AR, right? And this is the AR, you know. Then the volume is going to be AR dr. And the same here. If you have a cross section, intersection, this is surface area. So the volume is also AR dr. I'm going to summarize this. And the method it's not mentioned in the book is instead of a fixed plane, fix a line, you fix a point. If a fixed point, if the distance equals r, then you get around the sphere. Okay? And this is called the spherical shear method, which is not mentioned, but it's also useful, especially when you're trying to find the volume of the sphere. Okay? So this is a fixed point. Then if you have a solid here, you have a cross cut. You have a cut. Yeah, this is a part is AR. As long as you're not able to calculate this AR, then the volume is going to be integral of AR. Yeah. Okay. So the formula itself looks exactly the same. The question is, how do you calculate the intersection? Okay, which is surface. Surface, portion of surface on the sphere, portion of surface on the cylinder, portion of surface on the plane. Okay. We will only consider here. We only consider surface. We only consider solid generated by rotating a region around one fixed line. So that's the reason we just needed to consider, yeah, the cylindrical shears and all the disks. Okay. All right, so let's take a look at another example. The region is bounded by oops, not touch. The region is bounded by or equals, oh, I hate it. Okay, now I'm gonna sketch that. All right, so region is bounded by a curve. So still same region, but we are going to rotate. Let's see. rotate about the x-axis. Okay, so here's a picture. Okay. This is a curve, and that's the region. Okay, you rotate that region about, this is the y equals square x, about the x-axis. Okay, so that is a region we're going to study. Okay, so I can rotate about the x-axis. I can also rotate about y-axis. Okay, I'm going to do two problems. Okay, this is a line. Here's two. Okay. First of all, yeah, set up the formula for the volume using how many problems you can do. So rotations about, let's do about the x-axis. Okay, set up a two integral for the volume of the region. Okay. One is using, yeah, the disk looks like that. If it's about x-axis, from outside looks like a cylinder. Inside looks like that, right? Clear. All right. Then what you're going to do is you're going to how to cut the solid into many slices. You can use a flat knife parallel to the YZ plane. Okay. Or you can use a circular knife around the x-axis. So let's set up integral in two different ways. The first, okay, using flat knife, right? Using discs, because what you get is discs. Okay. So how do you cut? X is from 0 to 4, right? X from 0 to 4. So for an arbitrary point X, this time if you're using discs, they have to use the x-axis to cut it. Okay. Then you get this arbitrary point, you get this. Okay, so this is a disk. So the area is going to be denoted by x. So the volume is going to be integral from 0 to 4 a of x dx. So integral the area of the cross section. But how can I get this area? It's going to be pi r squared pi little r squared. So then you have to figure out what is r, what is little r at the point x. At the point x, okay, this is my r, this is my capital R. I think a capital R is always a constant, which is 2. So little r, if that is a point has coordinates x and y, so little r is going to be the y value. But we have to express as function for x, right? So it's going to be square x. Okay, then you're done. The volume is going to integrate from 0 to 4. And 2 square minus pi square x squared dx. So this is the formula for the volume. Second method, using cylindrical shears. Okay, I'm going to draw the picture again. So how do we do that? The axis is still axis, but we're going to use cylindrical shears. So you cut them, you get cylinders. Oops. Jesus. It's more and more unstable. Okay. So my all right. I have no idea. Okay, you go ahead and try and do it. Okay, set up. Okay, you draw the cylinder. And this is going to be up. Screen stops. I don't know what happened. All right, so you what you do is find the parameter. The parameter is radius. Okay, then find the area of the cylinder in terms of R. Then you integrate. Okay, so the volume is going to integral AR dr. I probably cannot use this this program anyway. Something's wrong. Okay, so the volume is going to be integral AR dr. So choose a point on the XY plane. Now, I give up, okay? I have to stop here, so I'm going to use a backbone. Stop. I'm going to delete this notebook check. Maybe that was. Do not have any open notebooks. My God, they're all gone. I even cannot find my notebooks. Oh, It's better now? Not. Who knows? All right. One more time. Okay. Delete that. Open it again. All right. What? My formula is gone. Okay. So the volume is going integral AR dr, right? This is R. The question is, how can I figure it out, right? So use a reference point is X and the Y. Okay, my R is the Y value. It's useless, okay? So let me close this, end of the meeting.